So another rule that's been developed, or method I should say, that's been developed is what's referred to as a half kVAR method. And this is associated with Dr. Granger. Dr. John Granger is the same person who is involved in writing the 451 textbook with associate Dr. Lee. And this actually works with any load profile, so we don't have to worry about whether we have distributed load versus spot load. It works with any load profile. And this could be used in conjunction with the power flow program. And so when you guys are doing your project, I'm basically asking you to take a look at applying this rule for the circuit you have, the buck swamp circuit. And what this method does is, given that you have a size of capacitor that you want to use in the circuit, what you do is you look at locating this capacitor bank at a location where the reactive power flow equals to 1/2 of the capacitor VAR rating. All right, so the idea basically would be that half this capacitor value would go downstream and half of this value would go upstream, right? And so the way the approach worked would be, first you pick a size. And so an example would be, say, pick a 1200 kVAR capacitor or whatever. And then what you do is you look at locations in the circuit where you've got 600 kVAR flow. And then you would pick the, what location would kind of make sense for that, where we'd get like the best results from. And then once you put this capacitor in, what this is going to do, this is going to change the VAR flows in the circuit, right? And so then if you want to put like another 1200 kVAR capacitor in there, and you look at another location where you have like 600 kVAR flow, you could play around with different sizes and stuff and see like whether 1800 would be better or 2400 would be better. But you just keep placing more and more capacitors in the circuit till you can't find any more locations that are going to be suitable for the size of the capacitor that you're going to be working with. And so let's suppose we had a 3600 kVAR bank in our previous example where we actually put it, right? And this is a pretty large value, but at least if we use this really large value, we're compensating all the load on the feeder, right? So we're going to get power factor and unity at the substation. But what I would be doing is I would be looking at a location where if I have 3600 divided by 2, I'd be looking at a location that had 1800 kVAR flow. So where does that actually occur in the circuit we were looking at before? Well, it actually occurs at the middle of the circuit, right? So basically I plop this 3600 kVAR bank right in the middle where I have 1800 kVAR flow. You can see what this is doing is our bars from the substation go to 0. And what we have for performance in this case is we got 151 kW, where the lowest voltage in this situation is going to be 0.993. Now, is this the lowest kW case we've shown so far? No, it's not. But again, you're able to pick and choose what size of capacitor bank you want to put out there. And we decided to put out enough capacitance where it basically sets the power factor that we're going to see at the substation equal 1, which a lot of utilities like to do. And so this is kind of a practical sort of method where, given you have a target as far as what you want for the power factor, you're going to place capacitors out there to hit that power factor target instead of just worrying about minimal kW losses on the circuit. So what if we were talking about 3 1200 kVAR banks, where we put those at? Well, again, you look at the kVAR flow, right? And so I've got 600 here, I've got 1200 here, I've got 1800 here, etc. So where would I actually put that 1200 kVAR bank? Where I would look for a location, I've got 600 kVAR flow, which is actually right here, right? And then if I put that bank there, then I would have another situation now where I've got 600 flowing in this direction. I've got 1200 flowing here. And so I could put another bank here at location 3. Then once I had that bank at location 3, then I would have 600 kVAR here. I'd have 1200 kVAR here. And I could put another capacitor right here at bus number 1. And so what this looks like as far as VAR mile profile now is what I've got here on this figure and on the top. Basically, I've got perfect compensation as far as the substation is concerned. That cap that's going to be at bus number 1, okay, is going to be potentially, backfeeding a little bit. And then what we see is this kind of gives us a very symmetrical type of VAR profile, where what we're doing in this case is we're minimizing the losses. So the loss is the lowest we've seen yet. I mean, this is 129 kilowatts. The voltage that we get at the end of the feeder is the best we've seen yet, which is 0.933. However, this is 3 times as expensive as putting a single capacitor out there. And so what you're generally going to see as I put more and more devices out in the circuit, that I get improvement, but the improvement for each additional capacitor isn't as great than the previous one. I get what we refer to as diminishing returns. So this is what you have to kind of be thinking about when you're doing capacitor placement, is you can look at a 1 capacitor bank versus 2 versus 3. You look at the cost and you look to see whether it's economically prudent in order to spend that additional amount of money for the benefits you get from the previous case. I've also programmed this up in WindMil, and I can put this up on I'll put this up on the Moodle side as well. Basically, I've got these 6 segments, and what I've done is I put capacitors at all these different locations where I switch these capacitor banks on and off as needed. So what I'm doing in this case is I'm putting in just a ZSM model. I'm basically, this line impedance represented a 4-aught positive sequence line. Again, I could plug the positive sequence numbers directly in. I run a balanced power flow in this case. And what I would get if I had no capacitors in the circuit is I'd get a worst case voltage of 0.935 with the losses of 273 kilowatts. You'll note that these are a little bit different than the Moodle spreadsheet results. And in fact, I've done a comparison here to show all the different cases we've looked at so far. And what you are going to see in here is that if you compare the spreadsheet to the WindMil analysis, that WindMil is going to give you slightly lower voltages and it's going to get slightly larger losses. Especially this is going to be the case if I'm deviating from bus voltages that are 1 per unit. So the lower the voltages get kind of dragged down, the worse this K-factor approximation gets in this case. And the reason this is happening is that if we look at load, we're using this constant PQ load model, right? I'm using this constant PQ load model. And if my voltage is below nominal, what this means is I'm going to get a higher level of current, because the current is going to be P minus JQ divided by the complex conjugate of the voltage. So with this constant power sort of load model that we use a lot of times, if voltage drops, current goes even higher, which causes even more voltage drop, which causes the current to adjust a little bit higher as well, right? And so because of this, typically for the really large voltage deviations, we don't get the same amount of accuracy. However, what you can see is once these voltages get closer to nominal, then the approximation looks a little bit better. So this is why you would use a power flow program instead of a K-factor spreadsheet. The power flow could maybe give you some, more accurate results for some of the extreme cases. But then the spreadsheet, you have the convenience of being able to do everything in the spreadsheet, which could include some economic analysis as well. WindMil does have a capacitor placement algorithm in it, where basically what you can do is you can set it up and you can hit the button and it'll actually give you some suggestions for the locations and sizes of the capacitors. In this particular setup here, what I've done is I've just said I'm looking for 3-phase locations on overhead and underground, and you have a minimum bank size and a maximum bank size. And so what this is, it's sort of a brute force technique. What it does is it basically looks at the impact of one capacitor at a time, starting at the minimum bank size, and then it just simply increases it by the kVAR increment value, and then sees, for all sorts of different combinations of capacitance, what would give you the best results. And it does it for 1 capacitor and 2 capacitor and 3 capacitors. And so basically all it's doing is just looking at all the different discrete options that are available. And then it just simply gives you what's the best result you would have from all the different discrete values. And so in this particular case, if I need to do 3600 kVAR of compensation, I've got a 1200 kVAR size, and what the program would recommend is it would recommend locations at buses 4, 3, and 2, which is not really the optimal, actually. And so this brute force technique, even though it's kind of convenient to run, is not really giving you the true solution in its case. It's not doing a mathematical optimization. It's just simply doing kind of like a brute force type of a approach. And whatever it converges to, it converges to. So next, let's talk a little bit about economic justification for this, because as I mentioned before, we could, have solutions that have 1 capacitor and solutions that have 2 or 3 capacitors. Well, which one will we choose, right? In what situations would I want to use 1 capacitor, and what situations would I go with 2 or 3 capacitors? Well, it kind of depends, okay? First of all, it depends on the benefits that you get from the additional use of capacitors. And I mentioned this before, all the different benefits that are accrued from capacitor placement. So we talked about the fact that if we reduce peak kW losses, that reduces the stress on our generation. So you're going to have what we refer to as released generation capacity. If I had power factor correction, if I'm reducing the kVA that's required of all my upstream components, say like my substation transformer, my transmission system, then I'm going to have release capacity associated with transmission and release capacity associated with substation. Sometimes those are 2 lumped together. Sometimes they're 2 different categories, but there's a benefit due to that. There's a benefit due to the fact that if I can reduce my I²R, there's going to be less energy associated with line losses. For feeders that are on my distribution circuit, there's going to be reductions in capacity required, so I get a release of capacity at the D level. And then also there's going to be voltage improvements. This is kind of hard to quantify sometimes if we're in the limits, but if I can keep from having to buy a voltage line regulator, then there could be some benefits there. So you have all these different benefits. And all these different benefits, a utility could actually calculate a dollar value associated with this. So what we're comparing that to is we're comparing that to the cost of the capacitors. And so obviously, yeah, there is a cost of the capacitor bank itself, the cans mounted on the frame. But then we have like all the mounting parts, and you got the fuse cutouts and surge arresters. You have to have a crew install that. This has to be maintained each year. Some engineers got to figure out what size and what location to put this at. There's a cost associated with design. And then if we have a control, this has to be set up with a radio, and then we have to set this up in SCADA, and we have to set the points up in SCADA and include this in our maps, etc. So you have various benefits and various costs, and we're basically looking at a situation, obviously, where for my solution, the benefits would outweigh the costs. You know, that's what we want to get to, is we want to get to a solution that I can actually justify to my management. So as far as the different costs are concerned, there's probably not a lot of costs you've actually thought about. You probably just thought, well, I've just got the cost of the hardware, and that's actually about it. When a utility puts a capacitor bank in the field, this actually becomes part of their asset base. And this is what a utility actually gets a return on investment on. This is how they make money. And so utilities do a lot of pretty detailed bookkeeping on their capital programs, their capital projects. And you can see that it just takes something as simple, what would be like a capacitor bank. And let's say this is a 900 kVAR capacitor bank in this case. Well, what you'd have is you'd have the cost of all the components, just as I just had mentioned before. I mean, you got the equipment itself you would buy that has the capacitor components, but then you would have to put a lightning arrestor on it, and you got to ground it, and you got fuses, etc. You've got the control for this. You're going to have to, you know, put a controller on it. You're going to have to mount it all up, you know, stuff like that. And so by the time you buy all the switches and everything else, then you might be up to, just based on materials, you know, maybe somewhere up to maybe like $7,000 or so, right? The other thing you would need to do if you're tracking your assets is you also need to capture the amount of labor, the amount of manpower you spent on it, right? That's included as well in the asset base. And so you look at the time required to do all this stuff, and then you would have a labor cost. And these are kind of old numbers here from maybe like 10 years ago, so they're not really updated. But you're going to have a labor cost associated with this. And then you have what's called indirect on your labor. And what the indirect is, when you actually have labor work on things, then you have to pay them benefits, things like that, Social Security, Medicare, et cetera, medical. And so this is what you might pay the person, but there's additional costs, which are indirect costs, which are overhead. And then the material itself would have to be stored in a warehouse, and somebody has to order it, and somebody has to track it. So there's an indirect cost associated with that. There's an overhead associated with just having the parts. And then your vehicle costs you money as well. If you have a truck that goes out there, you have to pay for the truck, right? So by the time you add all this up, then maybe you're up to maybe like about $11,000 as far as the cost of this installation, if you look at parts and labor. And this would be what gets tracked in, if it's a utility, in the utility asset database. And so all this stuff would have to be captured, and actually would be part of your net cost. All right. So let's stop here, and I'll talk about a little bit more specifically about how we could actually do this cost benefit analysis and what would actually go into this then.